Hey everyone, and welcome to The Explainer. I am so thrilled to have you here today. We rely entirely on the seamless flow of information, but have you ever stopped to think about the literal, physical machinery that makes your latest text message possible? It's kind of wild when you actually break it down. Today, we're going to explore the hidden, deeply physical realities of human communication. We'll trace this incredible arc from the earliest visual signaling networks right up to the massive, power-hungry cell towers of today, and ultimately figure out how we can build our own resilience when those modern systems inevitably fail. So I want you to start by asking yourself a really simple question. How much physical energy does it actually take to send a message? We're so used to just tapping a piece of glass and instantly reaching someone across the globe that we've kind of forgotten that communication is fundamentally a physical action. It requires structure, it requires energy, and the deliberate manipulation of the physical world. Whether it's a person physically moving their arms or a massive tower consuming megawatts of electricity, making that connection always demands energy. Here is our agenda for today. 1. Early optical telegraphs. 2. Railway hand signaling. 3. Modern cell tower anatomy. 4. Cooling systems and overheating. 5. When the grid fails. And 6. Emergency communication planning. Section 1. Early optical telegraphs. To really wrap our heads around the physical nature of our networks, we actually need to step back in time a bit to the late 18th century. Early messaging was incredibly mechanical. Invented in France in 1792 by a guy named Claude Chope, the optical telegraph, or the semaphore telegraph, relied on a line of physical towers spaced about 5 to 20 miles apart. Operators would literally peer through telescopes at the neighboring tower. When it was time to send a message, they had to physically move these massive indicator arms on their own tower to pass the signal along. To encode the text, these arms could be placed into 8 possible positions, locking in at strict 45-degree increments. Think about that. It was a massive physical exertion just to send a few simple words.
Section 2. Railway hand signaling.
And that highly structured physical movement wasn't just left behind in the 18th century. It evolved, and it became absolutely crucial to the railways. You have a really stark contrast here. On one hand, you've got those massive daylight semaphore systems stretching across the country with giant indicator arms. But on the other hand, you have the highly localized, really intimate physical signaling of the railway. Take railway signalmen in India, for example. They rely on specific, dynamic hand signals to safely manage these complex shunting operations in the rail yard. And when the sun goes down, or maybe fog rolls in and makes visibility terrible, they switch to physically waving hand lamps to signal and guide these massive trains. Both systems, whether it's the giant towers or the individual signalmen, rely entirely on precise, highly structured physical movements to communicate vital information. Section 3. Modern cell tower anatomy.
All right, so today we've obviously swapped out wooden arms and hand lamps for invisible radio frequencies. But has communication really become any less physical? Honestly, not at all. The sheer physical scale of a modern communication mast reaching into the sky is staggering. It's this massive piece of industrial structural engineering. These towers have to be built high enough into the air just to establish a clear line of sight, and they're capable of casting signals up to 20 miles in rural areas. They're loaded down with heavy panel and sector antennas, and they have to withstand tremendous wind and environmental stress. There's just no way around it. The physical footprint is absolutely enormous.
But here's the thing. The mast itself is really just the skeleton. At the bottom of that giant structure sits the actual brain of the operation. This is called the Base Transceiver Station, or BTS. The BTS is the ground-based equipment that actually does all the heavy lifting. It houses the radio transceivers that process, encrypt, and dispatch the radio frequency signals to and from your phone. It literally converts your voice into a digital format and sends it off to the mobile switching center. This little ground-level box is where the magic really happens. Section 4. Cooling systems and overheating. Now, there is a massive catch to having all this processing power housed in those little ground-based shelters. Because the base transceiver station is constantly processing thousands of concurrent calls, it generates a tremendous amount of heat. Without constant ground-based cooling systems, essentially heavy-duty fans and air conditioning chilling those enclosures, these delicate electronics would literally overheat and fry themselves, especially during the summer. These cooling systems aren't just a nice-to-have, they are absolutely mandatory for the tower to function at all, and fanning those systems requires a constant, heavy stream of electricity. Section 5. When the grid fails. Which naturally leads us to a pretty terrifying question. What happens when a neighborhood blackout strikes, and those essential cooling systems and transceivers completely lose power?
Well, cell towers do have secondary defense mechanisms, but they're definitely not infinite. First step, on-site batteries kick in the exact millisecond the grid fails. But they are just a bridge. They often only buy a 4 to 8 hour window of time before going dead. If it's a critical macro tower, a permanent diesel or natural gas generator might start up. Now, that can last for days, but only if fuel trucks can actually navigate blocked roads to refill them. Finally, carriers can deploy a COW, or cell on wheels, which is a mobile tower. But that's a reactive measure only brought in long after a disaster has already struck. Now, I'm almost certain you've experienced this incredibly frustrating phenomenon. Your phone shows full bars, but you still have absolutely zero service. No way to load a web page, no way to make a call. Why does that happen? Well, mainly for two reasons. First is the backhaul problem. Your local tower might be running fine on a generator, but if the fiber optic relay station 10 miles down the road lost its power, your local tower becomes an isolated island. It can talk to your phone perfectly, but it can't send that data anywhere else. Second is network congestion. Think of it exactly like a highway during a massive rush hour evacuation. The road is perfectly intact, but there are literally so many cars packed onto it that no one can actually move forward. The network's limited lanes simply fill up.
Section 6. Emergency Communication Planning. Because we now know that this modern infrastructure is honestly just as fragile as a 1792 optical telegraph, we have to take responsibility for our own connections. The best time to prepare for a blackout is definitely when the lights are still on. You need to build a physical emergency communications kit with a few very specific items. Get a high-capacity portable power bank, at least 10,000 milliamp hours, so really solid one. You need an off-grid power source, like a solar charger or a hand crank generator. This next one is absolutely crucial. Write down physical copies of important phone numbers. Your digital contacts are completely useless if your phone is dead. And finally, diversify your tools with an emergency NOA weather radio and a backup device, like a satellite messenger or a two-way radio.
Now, if you do find yourself right in the middle of an outage, here is the absolute perfect step-by-step strategy for conserving your phone's battery when the towers are struggling. Step 1. Immediately switch to power saving mode to kill all that unnecessary background activity. Step 2. Set your screen brightness to the absolute minimum. Your screen is far and away your biggest power drain. Step 3. Switch to airplane mode. Look, if the network is down, your phone will drain its battery super fast, just trying to desperately shout out to a tower. Put it in airplane mode and only turn it back on once an hour to check for messages. And remember this pro tip. Use SMS text messages instead of voice calls. Texts are these tiny little packets of data that can squeeze through the small gaps in a congested network way easier than a demanding voice connection. We've covered a really incredible journey today. From the 18th century operators physically pulling levers on those massive optical towers, to railway signalmen waving hand lamps in the yards, right up to the massive 5G backhaul cables and those extremely vulnerable cooling systems of today. But the core lesson remains totally unchanged. A chain is only as strong as its weakest link. Communication has never been magic. It's a fragile, deeply physical chain of infrastructure. So I'll leave you with this final, somewhat provocative thought to mull over. When the local grid fails, and the tower batteries drain out, and those critical cooling systems finally shut down, is your personal communication plan ready? Don't let a single point of failure isolate you. Take what you've learned from this explainer today, go build that emergency kit, and ensure you remain connected when it matters the most. Thank you so much for joining me on this deep dive, and I will see you next time.